Hi everyone. So welcome to the post-lunch session. These are we are going to have 4 lightning talks, whatever that means. So 4 talks, roughly 15 minutes each in the next hour. So the first talk is by Ashutosh from TIFR.
Okay, hi everyone. I'll be talking about some work from a couple of years ago on algorithmizing the multiplicity Schwarz-Zippel lemma. This is something that, those of you who were around last week, I think Mrinal maybe name dropped it. So this is, we'll talk more about it now. This is joint work with Siddharth, who's he's now in TTI Chicago. He was a grad student at TIFR, and Prahladh and Mrinal who are here. So what are we talking about? First, let's start with a familiar object for us at this point, the Reed-Solomon code. Someone said yesterday, the king of codes. So till now, we've been seeing evaluations over the whole field, but there's no reason why that has to be the case. You can just take some set of some size n, and the code consists of evaluations of degree D polynomials on this set S. Why is this a code? This is a code because if you think of this object, this collection of evaluations for 2 distinct polynomials, then if they agree on more than D places, that means P minus Q would be 0 on more than D places. And by the degree maxim, which is that a degree D polynomial which is non-zero can be 0 at most D places. That means P minus Q would be identically 0, which means that P would equal Q. So if P and Q are distinct, then they have to disagree on at least n minus D places. So this is why the Reed-Solomon code is a code. But we can actually, what I just called the degree maxim, we can make it a little bit more general. We can say that, in fact, the sum of multiplicities of zeros at various points, that is also at most D. So this naturally gives another code, which is a univariate multiplicity code, which is evaluations of a polynomial and its derivatives up to some order S, which we can choose. This is also a parameter of the code. So we have the Reed-Solomon code, and we have one generalization, which is the univariate multiplicity code. There's another way to generalize this, the Reed-Solomon code, which is to make it multivariate. So m-variate polynomials, I should have said. Evaluate m-variate polynomials of total degree D on, again, I think yesterday and last week we saw it on a whole field, but it can just be any set S to the m. And why is this a code? This is a code because of something called the Schwarz-Zippel lemma, which says that these evaluations must differ on at least n to the m is the whole thing, 1 minus d by n fraction of the location. So this is why the Reed-Muller code is a code. So what have we seen so far? We've seen the Reed-Solomon code, one generalization, which is adding multiplicities, and another generalization, which is making it multivariate. And the distances are as you can see over there. So the question is, can we do both of these generalizations at once? Can you make it multivariate as well as adding multiplicities? And if you were to have a guess at what the distance might be, well, we want there to be an n to the m, and then we would guess that there's a 1 minus d by n is similar to the multiplicity code. So the question is this true? And the answer is yes, otherwise there would be no talk. This is true. There is a multiplicity Schwarz-Zippel lemma. It is due to Dwyer, Koparty, Saraf, and Sudan from, I think the journal version is 2013. And what does this multiplicity Schwarz-Zippel lemma say? You have a multivariate polynomial, degree D, m variables, and you're concerned about a set of size n. And we will say that for a point A in this big grid, the multiplicity of P at A is the order up to which all partial derivatives of P are 0 at that point. Then summing up the multiplicities over all the points, it is this thing, d times n to the m minus 1. And the part that's relevant to us is, if we were to give S derivatives, then those objects cannot agree at more than d by S places. So basically, for multivariate multiplicity codes, they do have this distance that we had predicted, n to the m times 1 minus d over ns. Okay, great. But this is a workshop on codes. We are concerned about codes. So let us look at some of the unique decoding algorithms that exist for these codes. For Reed-Solomon, we saw Welch-Bellecamp. There are many, many more. For multivariate, which is basically Reed-Muller codes, like we saw yesterday, the decoding algorithms for over the whole field, they are really old, many decades old. But some of you might be surprised to know that over arbitrary sets, we actually didn't have an algorithm, a completely general algorithm until 2017. This is due to Kim and Koparthi. For univariate multiplicity codes, we have Koparthi, Guruswami, Wang. Those are in fact actually list decoding algorithms. So the point that I want to stress here is that these algorithms don't assume the theorem or the lemma in question that actually gives the distance. So what they are actually is an algorithmic proof of the distance theorem. For instance, the Kim and Koparthi paper, which I do recommend reading it, it's a very nice paper. It doesn't assume the Schwarz-Zippel lemma. Instead, it just proves if there is a polynomial p within this, half the minimum distance of this received word, then the algorithm finds it. And the algorithm returns only one thing, and therefore the Schwarz-Zippel lemma must be true. So the Kim and Koparthi algorithm is an algorithmic proof of the Schwarz-Zippel lemma. So we are interested in getting something similar for the multiplicity Schwarz-Zippel lemma that we just saw. And that is what this work is. It's a unique decoding algorithm for multivariate multiplicity codes, and also an algorithmic proof of the multiplicity Schwarz-Zippel lemma. So that is what the result is. So slightly less than half the time left. Let us take a quick look at the algorithm. So it's based on Kim and Koparthi's Reed-Muller decoder. So let's see how this proceeds. We look at the m equals 2 case. It's fairly simple to understand. It's also, you can think of it as a remark which he made yesterday, which is it's sort of Reed-Solomon tensored with Reed-Solomon. So what we're going to do is, so we have a grid S cross S, and we have some received word, one for each of these, and a degree parameter D. And we're trying to find a degree D polynomial P, which is sort of close to this received word. So what we're going to do is, we're going to go in D+1 phases. We're going to write P this way. We're going to separate out the Y variable. We don't know P yet. We're going to separate out the Y variables. So each term is PL of X times y to the d minus L, and we're going to find each PL one by one. And in fact, for now, we're going to just focus on finding P naught, and then you can sort of recursively do the rest. You can subtract it, divide it, keep going. So this is how the algorithm is going to go. And how are we going to find this P naught? First, we're going to fix a column. So this, if you were to restrict the corrupted word to this column, then you have a univariate in Y, because you fixed X equals A. So now that you have a univariate, what can you do? You can do Reed-Solomon decoding to this column. You will get some polynomial in Y. Let's call it GA. But remember, we're trying to get P naught. P naught is a constant. So this polynomial has the constant term GA. So this is sort of this column's guess for what the constant might be. So the basic idea here is that there's going to be errors all over this grid, right? So it's not the case that the errors are going to be evenly distributed on each column. Some of them are going to be more corrupted than others. So it wouldn't be correct to just consider every GA sort of with equal confidence. We should be having more confidence in some and less in others. And how do we decide this? We have this candidate constant term from each column, this GA. But we also have a bit more information, which is sort of the uncertainty, which is how many errors we had to correct to get this polynomial GA in the first place, which is the distance between RA, which is the thing that you received, and GA, which is the thing that you got after Reed-Solomon decode. So now that we have this little bit of information, we're going to guess that, okay, if in a column we had to correct a lot of errors, we are less confident in that column. Whereas in some column we had to correct only a few errors, we're going to have a little more confidence in that column. So, but we said the other way, we're going to have high uncertainty if we had to correct more errors. So what we're going to do is we're going to pick a threshold and then erase the locations, the columns with higher uncertainty than that threshold. And then now do a sort of Reed-Solomon decoding to combine the guesses from each of the columns. And there are n possible thresholds, n+1 maybe. So you need to show that there's one threshold which makes it possible for you to decode. So So what are the subroutines that are going on in this algorithm? There's one ordinary Reed-Solomon decoder, which is just the column decoding. And then you have a weighted Reed-Solomon decoder, because for each column, you have this guess, the outcome of the Reed-Solomon decoding, and then the constant term that it has. And you have a weight, which is the uncertainty in that column. So a weighted Reed-Solomon decoder for that. So for both of these, any Reed-Solomon decoder for an arbitrary evaluation set will work. For instance, Berkeley that we saw. So our algorithm proceeds similarly. So it goes in D+1 stages, and we're going to again decode a column, but since it's multiplicity codes, the column decoding is going to be univariate multiplicity decoding, and we're going to assign an uncertainty parameter, and then we're going to combine the information from all the columns to get that particular coefficient, and then go to the next stage. So the subroutines are one, a univariate multiplicity decoder for the columns, and then so this proceeds similarly to Berkeley. And then a weighted univariate multiplicity decoder. So combining the weight, this uncertainty quantity that you have, with its guess for the coefficient. So, but remember this time we're dealing with multiplicity. So there's S levels, right? The S derivatives that you have. So each of these has n possible thresholds, which gives n to the s possible thresholds. And we are going to assume monotone for certain reasons, but it's still O of n to the s monotone threshold. And you have to prove that at least one of these works. So this is the main technical piece in this paper. So in summary, we have an efficient, mostly in settings that come up in real life, algorithm to unique decode multivariate multiplicity codes. And it also serves as an algorithmic proof of the multiplicity Schwarz lemma. Some further questions: improve the running time. So there's an efficient with an asterisk. Basically, we work with the case where the S parameter is a large constant. In other cases, it might not be polynomial time, strictly speaking. So can we improve it? List decoding, there is a list decoding algorithm already. That's also Bhandari, Harsha, Kumar, and SS Sudan, not me. That does list decoding, but with some caveats. And another interesting question might be, so if you remember the proofs that we saw of Sudan and Guruswami Sudan, they proceed quite differently, right? They use what we call the polynomial method. And also those don't proceed in this D+1 phases, right? They just find the polynomial sort of all at once. So it might be interesting to understand Kimco party as well as this one, why these have to proceed this way, and is it intrinsic to something about Reed-Muller codes and multiplicity codes, or is there some other way we could possibly think about this decoding problem? So that's this one. Thanks.
Is by Rohit from IT Jammu.
Thank you. I'm just presenting to joint work with Fernando and Prashant on the majority logic decoding of a fine Grassmann code over non-binary fields. So what is the projective system? Just as a collection of endpoints, not necessarily distinct, in any projective space EKN, it's called projective NK system. If this collection is not contained in any hyperplane, then it's called non-degenerate projective system. So if suppose P1, P2, Pn is a collection of non-degenerate projective NK system, then we can construct a code through evaluation map of homogeneous polynomial of one degree of k variable in this way. And what is the interesting thing in here? There is one-to-one bijection between non-degenerate projective system and non-degenerate linear codes. So the minimum distance find out of linear code is turn out to finding the maximum intersecting point in hyperplanes. So Yeah. So one important object in algebraic geometry is Grassmann. Grassmannian is just as a collection of all L-dimensional subspace in a fixed vector space FQN. So through Pilker embedding, we can see GLM is we can embed in projective space M choose L-1 as a non-degenerate projective system. So we can associate a code through this object. And Ryan and Nogin in 93 for general Q, and Ryan computed for binary cases to basic parameter of this code. And one interesting thing, give this object as a determine the NK MDS linear codes, number of MDS linear code is equivalent to determine the number of points in Grassmannian, which is all the Pilker coordinates are non-zero. So yeah, what is the affine Grassmann? So we set L is less than L dash, and M we choose a L plus L. So A delta we denote the set of all L by L prime matrices, and we can identify these matrices as a points of Grassmannian. Through this choose a matrix A, we can associate as a Grassmannian as a point as a row space of A by adjoined by identity matrix of L by L. Actually, just we can expand the L by M matrix, adding last L column as a identity matrix in A. So A adding identity matrix is a rank of L matrix. So it's a give a row span, just give a L dimensional substrate. So we can identify matrices as a points of Grassmannian. So it's a A delta we can think about as a open set of Grassmann variety. So we can also associate the algebraic geometric code through this object. So more explicitly, how to construct this code. Suppose X, let X be a delta variable X matrix L by L, and FLM is just as a FQ linear span of all minors of X. So we can embed, evaluate these polynomials in this way. If we enumerate all the points of A delta, P1, P2, P, Q raised to power delta in this way. So the image of this evaluation is called affine Grassmann code. And support is just as it defined by where polynomial is not vanishing, that's points are called support. Yeah. So this code is introduced by Beelan, Korpede, and Hall in 2010, and they computed basic parameters. And also they study the dual of this code. And this shows that if Q is not non-binary, then minimum distance of dual is 3. If Q is equal to 2, then minimum distance are 4. And Korpede and Kleipa also study the automorphism groups of Grassmann code and as well as affine Grassmann code. And they show that these groups are acting transitively on the coordinates of these codes. So now I'm going to what is the majority logic decoding. So yeah, I think everyone know. So I'm just recall, we can construct a large set of parity checks where each ith column of that matrix H is 1 and other column which at most one non-zero entry. So if length of this set is J, then we can correct and we construct as I say this type of set in for each coordinate, then we can correct J by 2 errors. So yeah, Beelan and Singh, they proposed the decoder for Grassmann code, and they using the idea using for geometry of Grassmannian, and this shows that asymptotically they correct up to d by 2 raised to power l plus 1 errors. And here I'm just not going to geometry, but I'm just algebraic point of view. So now for rest of the, I am assuming Q is non-binary. So for us, Q is greater, far field Q is greater than equal to 3. So if Q is greater than or equal to 3, then we can construct a set GQR, is a tuple of A1, A2, AR, where AI are the set of two elements, non-zero two elements of FQ, such that any two elements of AR and BR in GQR, there exists some coordinates AI and BI such that AI intersection BI is empty. So this set have at most cardinality Q minus 1 by 2 raised to power R. Yeah. So let VR and WR be R-dimensional linear subspaces of FQL and FQL dash respectively, and fix a basis of VR and WR, then and choose a tuple as previous. So we can construct a set MB B prime AR such that AI TI transpose YI, where AI belonging in AI. So we can see this is not a L by L prime matrix, as well as these matrices have rank R. So if we take two different bases of WR, then we can see these sets are disjoints. And also if we take two different elements of GQR, then also these sets are disjoints. So now just I'm going to how to construct a parity checks for affine Grassmann codes. So if we restrict affine Grassmann code in this set of MB B prime AR union 0. So this, after restricting our affine Grassmann code in this set, we get a code of length 2 raised to power R plus 1 and dimension is 2R. So we can see after restriction of this code, it is just as a hyperplane of this dimensional spaces. So exactly they give a one parity checks, which is just as a equation of hyperplane. So actually, and then we can pull back this code word in affine dual of affine Grassmann code. So we get a parity checks which support lie between in this space. Also we can see zero matrix always lie in support of W. So if we now our question is turn out how many this set is construct. So yeah, so total number of this type of set we can construct in this number. So this quantity turns out from cardinality of GQR, and this quantity turns out to how many bases we can choose of WR, which is at least one coordinates are different to another basis. And these quantities turn out to how many VR in line FQR. So yeah, so we can, if we, and here we can see zero matrices lie in each parity checks. So, and since both sets are disjoints, so only zero matrices lie in support of each subset. So these parity checks are orthogonal. So yeah, but we can use the automorphism group of affine Grassmann code. It's well known. So we can construct for each coordinates of these number of parity checks. So asymptotically, we can correct up to 1 by 2 raised, or d by 2 raised to power L plus 1 error through in this way. But here, yeah. So yeah, there is some differences. Yeah, thank you.
Questions? Okay. Yeah.
I don't know. I don't know what is practically, but I'm actually geometric point of view, this is nice, and geometry also is nice of a fine Grassmann code as well as dual of fine Grassmann code. So I'm just looking through as a geometric point of view.
Further questions? Okay, if not, let's. Talk of the session is by Amolak from University of Waterloo.
Okay, so I'm going to talk about quantum circuits and how certain problems in quantum circuits benefit from Ramanujan graphs and then later Ramanujan complexes. So the first slide is just like a crash course on quantum circuits. So qubit is the basic unit of information for quantum computing, and it's a unit vector in C2. So you can think of it as some alpha beta column vector. Then you have quantum gates, which perform operations on these qubits. These are unitary matrices with complex entries. And then using these gates, you create circuits. So you just string together these gates and you get quantum circuits. And these quantum circuits are finally then used to implement some quantum algorithm. So I'll call this U target in the talk. And you can think of the quantum algorithm as Shor's algorithm or whatever your favorite quantum algorithm is. And the problem is called circuit synthesis problem, and that's what I'm going to focus on. And the problem is the following. Design a circuit C that realizes U target using a universal gate set G. So you want to compile U target using words from G to realize, you basically want to realize U target. It looks something like this. U target is basically equal to G1 to Gn, where Gi are in capital G. So you're compiling U target using words from capital G. Okay, so the input to this problem is this triple, your target unitary, which realizes, it's a big unitary. So this is the one that realizes some complicated quantum algorithm. G is your universal gate set, and epsilon is your precision parameter. And the output, the desired output is short circuits, so short words over G. Okay, so now this is very similar to the classical problem, okay, where you're trying to, say, realize some Boolean function using some universal gate set like NAND. So trying to use NAND gates to realize some Boolean function. There are two differences. First, because the unitary group is an infinite group, you can only realize in general to some epsilon precision. Okay, so you can't do exact decompositions. And the second difference is that usually universal gate sets in quantum computing have more than one generator. So NAND was a single generator. This is usually not the case. Okay, so let's now simplify the problem in three ways. Okay, we'll first set epsilon to 0. So now the question becomes which unitaries are exactly implementable using capital G. We'll also set U to be just 2 cross 2 matrices for simplicity. Okay, so you're trying to realize a 2 cross 2 matrix using a universal gate set, and we fix the universal gate set in our case to be generated by these matrices H and T. So your H matrix is like this thing. Okay, so 1 over root 2 with these 1s and minus 1s, and T is a diagonal matrix with omega 8 on the diagonal. Okay, omega 8 is the primitive 8th root of unity. So this question about which unitaries are exactly implementable using capital G was completely solved by Klushnikov, Maslov, and Mosca in 2012. And they had this description of it. So they said that the group generated by these matrices H and T is equal to the 2 cross 2 unitary matrices with entries in this very specific ring. Okay, and the proof was constructive. So what does that mean? That means that if you're given any unitary matrix with entries of this type, I can realize it using words from H and T. Okay, now this is actually a surprise, and it's a surprise in two ways. So such groups like U2 with some Z1 over root 2 I type of groups are actually called arithmetic groups. Okay, and giving generators for arithmetic groups is actually very hard. There's no systematic way to do this. Okay, furthermore, using those generators to solve the word problem is also hard. Okay, so there's no real general way to do this. And somehow quantum information magically could come up with a natural set of generators for this group, for this arithmetic group. And synthesis was able to tease out how to solve this word problem. Okay, so now you might say that, this is a very strong simplification you made. You made 3 simplifications here. This is so the point is the initial problem that I introduced on the previous slide was defined by this triple, UG and epsilon. What you can do is you can take, so there you have an arbitrary 2 cross 2 matrix, okay, and you're trying to realize that over some universal gate set. So what you do with that arbitrary unitary matrix is that you take each entry, round it off into this ring, and then do exact synthesis. And this actually works very well in practice. Okay, so seeing these surprising developments that arithmetic groups and those word problems enter Peter Sarnak and Ramanujan graphs. So Sarnak wrote this letter to Scott Aronson and Andy Pollington when these results were brought to his attention. And in this letter, he studies the synthesis problem, but now through the lens of the LPS construction. Okay, so he makes use of the LPS construction, which is originally the construction to give Ramanujan graphs. And he converts the word problem of exact synthesis into traversing the Cayley graph of the underlying group. Okay, so H and T has a Cayley graph associated to it, and traversing that Cayley graph solves the word problem. Okay, now, so one desired output was that you want short circuits in the synthesis problem. He showed that expansion properties of this Cayley graph tell you about how short the circuit will be. So good expansion properties for Cayley graphs imply short circuits. So here is an example. So this is an example that actually first showed up in LPS. And then he was able to convert this into a gate set. So this is called the V basis gate set. Okay, so S1, S2, S3, and their inverses form a group. You can think of these as gates. So this is your universal gate set. It is universal. And this has the following equality. So the group generated by S1, S2, S3 and its inverses is equal to U2 with now entries in a slightly different ring, but it's still an arithmetic group. Okay, now he shows, and this is one of the things that LPS really studies, is that this group has an action on a 6 regular infinite tree. Okay, and this 6 regular infinite tree comes from the Cayley graph of this group. So, you can see that there are 6 generators, that's why the degree is 6. And finding such a tree on which this group acts nicely is actually the hard part. Okay, but because of LPS in this case, and because of the letter, we know that it acts on T6. And then navigation on T6 is basically equivalent to solving the synthesis problem. So finding certain paths from, say, the origin in this graph to some other point on the graph solves the word problem. And the edges then are the sequences of gates that you need to realize your unitary. And expansion properties of T6 will tell you about the word length. So in fact, this T6 has very good expansion properties. And that's why using this gate set, you output very short circuits. So it's a very nice gate set. Okay, so now we wanted to sort of mimic this idea of quantum information being useful to find generators and solve the word problem. So the question is now, can quantum information tell you other generators for arithmetic groups? And the answer is yes. So all you have to do is you have to move everything to 1 dimension higher. Okay, so now we'll be in qtrits. A qtrit is a unit vector in C3. And the circuit synthesis problem there is that you have some target unitary you want to compile. It's a 3 cross 3 unitary. You have a universal gate set capital G. This is some universal gate set using 3 cross 3 unitary matrices. And then we could show, so this is our first result, that we could show that HDR, which are some unitary matrices that have a very natural interpretation in quantum computing, generate this arithmetic group U3 with entries in Z1 over root 3 and omega 3, where omega 3 is the primitive 3rd root of unity. Furthermore, we were able to conjecture and modulo an obstruction show that H and curly D, this time curly D is this matrix, generate the group U3 Z over 1 root 3 omega 9. Okay, so ninth cyclotomic is coming up here. And because there was this obstruction, I wrote an email to Shai Evra about asking if one could do this. Is there some like high level machinery using these expanders which one could just show this unconditionally? And he actually wrote back with a paper. And he solved this problem using the theory of Brouhart-Titz building. So this is kind of complicated. It uses a lot of very modern machinery. But he was able to solve the word problem. And in fact, what we conjectured was true. And he later goes on to show that the expansion properties for this gate set is actually very nice. So in the previous slide, the gate set was called golden gates. It's slightly worse in this case, so they're called silver gates, but you still do pretty well. So after this happened, we finally decided to learn some stuff about these higher dimensional expanders in buildings. And so this is our attempt at using these things. So this is work in progress with Mark, who's an undergrad, Nihar, Mosca, and Yard. And we study the problem of this gate set, the first one, using machinery similar to the ones that they use here. And again, the main problem here is so this is the arithmetic group in question. And if you want to try to solve the word problem efficiently, you need to find a simplicial complex on which this group acts nicely. Okay, and our main result was that this arithmetic group and this generators act on a 4 regular tree this time. And they do so nicely, and we are now studying their expansion properties. So that's all. Thank you.
Yes.
You solve the word problem. Is it just in terms of having length bound on building this path, or you actually have a computational bound?
So no, it's about the length. The length, yeah.
It could be computation.
Yeah, it's a short path. Yeah.
You all?
Yes. We are hopeful that there are more such things. So one thing which we sort of did not talk about is multi-qubits, which is where actually what you do algorithms on. That also has an arithmetic description. But there are some more complicated problems, like you have these ancillars, which you need for the arithmetic things. Now, in buildings and things like that, ancillars are not a thing. Like, how do you model an ancillar? So that's sort of something. But yeah, we are hopeful and excited. Hopefully, there'll be something like that. Yes.
So would it make sense to consider a version of the problem where you are given it as a word in one generating set and you want to construct the same operation as a word in a different generating set?
Yes. And this naturally happens when you're trying to shift architectures. So practically, maybe you have some superconducting qubit thing where you're allowed some gate sets more simply. And then you want to shift generators, and maybe there's some other physical platform in which you want to do it. So this R gate comes up in topological quantum computing. So if you want to do it there, then you want to shift these. And yes, then that's a natural problem to consider. Oh, yes. Oh, yes. That's, yeah. There are some results going towards this, yeah.
Other questions? Okay, let's thank Kamal.
So hello, I'm going to talk about sparse cuts in hypergraph using random walks on simplicial complexes. This is joint work with Anand Lewis and Ramesh Paul. So the aim of this talk is to sort of relate this notion of hypergraph expansion to this spectrum of random walks and the local spectral expansion of a complex. Okay, so since we have not seen hypergraph expansion yet, let's go with that. It's similar to graph expansion. We look at the edges cut, measure its weight, and divide by volume.
and look at the least expansion in this way. Okay. So, and the notion of sparse cut would be to find the set with the minimum expansion. Okay. So for graph, we have this clean sort of inequality called Cheeger's inequality. It's sort of similar to expander mixing lemma. It relates the second eigenvalue to the expansion. So if you look at this right-hand inequality, this is sort of an algorithmic inequality. We actually produce a cut to show this inequality. And these people, Aurora, Borak, and Schroeder, showed that you can actually sort of do this even if you have looser bounds, in the sense that if you have a lot of large eigenvalues, you can find a small sparse set. Okay, so why can't we do this with a hypergraph? One problem with the hypergraph is, well, we don't know what's the correct notion of spectra of a hypergraph is, right? And one approach was to actually define some Laplacian operator and consider its eigenvalues. The issue is such an operator is not linear on every hypergraph. So we'll move to the corresponding simplicial complex and analyze the random walks on this simplicial complex to get a cut instead, right? Okay, so we all have seen simplicial complexes in this room. Like, I've been seeing it for the last 7 days. So I'll just note that I'm using dimension to denote the cardinality of the face, not like the geometric dimension, okay? And I'll be dealing with pure simplicial complexes. Okay, so from a hypergraph, weighted hypergraph, we would get a corresponding simplicial complex by just putting the same weights on the top face and then subsampling, right? Okay. Okay, so we have seen up-down walk. I mean, this is the up-down walk, picture of an up-down walk. But there's another non-lazy walk we can define on a simplicial complex. So what we can do is define this swap walk from level I to level j. And this swap walk is first defined by first moving to a larger face of dimension I plus j. And this is the same probability as doing an upwalk from sigma to tau plus sigma. And then we deterministically go to the complement. If you sort of look at j equal to I equal to 1, this is the random walk on a graph. Okay? Okay. And we were sort of motivated to do so because we wanted to solve these problems called constraint satisfaction problems. And there are, so these problems capture a lot of problems in CS, like max cut, 3-sat, linear equations, even decoding codes reduced to solving CSPs. Okay. So generally speaking, we have n variable. The problem is that we have n variables and we want to assign some labels to each of the variables. And we want to do so by, while maximizing the number of constraints satisfied, which are the relations over these variables. And if all these constraints are k-ary, we call this KCSP. Okay. So let's just go over that sort of work which was already done before we try to do all this. So there was this SDP-based algorithms which solved this problem, two CSPs, if the number of large eigenvalues were small. So it was, it's sort of a looser notion of than having expansion, where we have exactly one small eigenvalue, large eigenvalue. And then the idea was to sort of divide any graph into these pieces where we can solve these individual pieces and combine them. So for KCSPs, a similar algorithm was given on splittable hypergraphs, and people who were in the school saw this notion of splittable hypergraphs in context of codes. It's really a very similar algorithm, right? Okay. So the notion of splittability is, so we actually talk about splittability in terms of like the threshold rank, which is the number of large eigenvalues instead of expansion. Let me sort of define formally what we mean by splittable hypergraphs. So let's say we have a hypergraph, which is, and the corresponding simplicial complex is X. And we will call it tau R splittable if for all L, the L to K minus L swap walk has R eigenvalues larger than tau. We have to go to the swap walk version of this because we are not in a partite case like we were in the talk by Madhur. Okay, so now the question is, can we actually use random walks to compute these sparse cuts, right? So the answer is no. We have, so firstly, let me give you a hint why the answer should be no. We already have complexes which have like sort of constant expansion and bad link expansion. Okay. So one example is this, where this has this very dense instance of hyper edges. But if you look at the link of the central K minus 2 vertices is just a cycle. So the expansion is very small. But the notion of splittability is even weaker than the notion of link expansion or local spectral expansion. So we do not immediately get a separation between hypergraph expansion and link expansion from the previous example. So we have to work a bit, but we are able to show that there is a hypergraph with that expansion at least 1 by k. And all the soft works with between 2 and some other dimension L are non-expanding, or rather have a threshold rank R, and also 1 to k minus 1 has a threshold rank R, which sort of gives us that all the L to k minus L random walk have threshold rank at least R. And it's a very simple example, actually. We just have a petal-like hypergraph, and depending on R, we'll put more petals here. The point is, if you try to do a random walk starting from any of the petal, it won't be able to escape because there's just only one thing in the center. So, and that surprisingly, this example also works. Not surprisingly, but yeah, it also works for up-down work. And that's all I had. Yes.
Questions for Arka?
Irregular in the sense of, okay, I see. Yeah. So you would want regular a version of this example, maybe. Okay. Okay. It's actually a good question, I suppose. Thanks. Okay. Bipartite graph. Right. Okay, I see. Yes, probably. I guess.
So yes, my question is there any relation either with 3D? So 3D is known that relation of text.
Three what?
3D.
I don't know what I thought three it said, but regarding your question about expressing. Tree width, okay. Tree width, okay. Okay, I see. Okay.
Sorry.
Oh, no, that's fine.
If 3D is small, then
Okay, yeah. So three widths are very similar to threshold rank in some sense. I mean, they have some similarity, but this is like a spectral version of three width in some sense. And that's sort of the kind of idea I have about three width really. But yeah, probably we can think about okay. I don't have a version with three widths in mind.